Hey everybody. Sorry, I think I might have accidentally ended the other meeting and started this one anew. Apologies if that's the case. It's not my intention. Let's pin my video. Get my screen looking right. How's everybody doing? Let's see. You guys are like fine. Let's see here. So before we get started here, I just want to say I know FAM's class is going a little bit slow. We're probably going to start getting ahead of that class in the co-class just because I want to make sure you guys see all the material that you need to be seeing, even if you're not there in FAM's class just yet. Eventually you'll get there. With that said, are there any questions about the exponential growth and decay stuff that you guys have been talking about in that class? It's okay if there aren't. I just want to make sure I kind of give you guys the opportunity to ask before we get going with stuff moving on into chapter 5. Let's see here. All right. Oh, sure. I was waiting until more people were in to post it, but yeah, there's the link to the sign sheet. Please sign in or fill it out only once. I don't think anyone in this class has, but a couple of my other classes have accidentally filled it out twice, so my counts have been off. I'm like, well, that seems weird, but it's not too big a deal. So not seeing any questions about exponential growth and decay, which is perfectly fine. I think we should start talking about antiderivatives and integrals more wholeheartedly. And there's a few things to say. So yeah, let's see here. Sorry, it's a little warm in here. So I know you have words. I posted a quiz for you guys. It's due tonight. There's a lot of instruction in the quiz, so you definitely should read through it because it's trying to kind of give you an idea of how things should work. But let's kind of talk about the notation stuff. So I know we talked about this last week, but I want to reiterate. When someone wants you to find an antiderivative of a function, the way they're going to write that is the easiest for them to write it is the following way. The antiderivative of, I don't know, something simple like x to the 8th with respect to x. So all these symbols mean here, those symbols are just instructions that say find the antiderivative. Also, let me make sure my volume is on. Yeah, okay, so if you guys talk, I'll hear you. Which is fine, you should talk. If you have questions, feel free to save them or type them, but I'm more likely to hear you. So if I'm trying to find the antiderivative of x to the 8th, well, for powers of x, we have this nice, what I like to call anti-power rule, where the regular derivative power rule, you bring down the power and you subtract 1 to get the new power. For the antiderivative power rule, we're going to do the reverse things in the reverse order. We're going to increase the power by 1 and then divide by the new power, which is going to be, and of course, we're going to add on a constant because the derivative of a constant is 0. So any function, x to the 9th over 9 plus any constant number you like would be an antiderivative of x to the 8th. So this is generally how we're going to write this kind of thing. if there's something else I want to see. Oh, important to note, once you have taken the antiderivative of the function and found the function that's the antiderivative, you no longer need to write this symbol or this symbol, right? Those are just kind of there to tell you to take the antiderivative, and once you've done it, you no longer do it. Just like if you're taking the derivative of x to the 7th plus tangent of x, once you take the derivative, you no longer write this symbol that means take the derivative. Right, we just get the derivative over here. So that's kind of the basic idea, the antiderivative of x to the 8th x to the 9th over 9 plus c. And when we're finding antiderivatives, the answers are always functions. So if I'm going to find, say, the antiderivative of e to the x plus, I don't know, something like, I had to get an example in my head, I don't know, cosine of x plus x squared. So just like with derivatives, antiderivatives, if they're added or subtracted together, you can antidifferentiate them piece by piece, right? If I was differentiating e to the x plus cosine of x plus x squared, my derivative would just be the derivative of e to the x, which is e to the x, plus the derivative of cosine, which is negative sine, plus the derivative of x squared, which is 2x. But since I'm doing the antiderivative, I'm going to do the antiderivatives of each of these functions. So it's going to be the, in fact, you could, so normally I wouldn't write this next part, but I'm going to do it this time. You could totally break this up as 3 separate antiderivatives. Or if you prefer, you could say 3 separate indefinite integrals. Like those terms are pretty interchangeable. Indefinite integral and antiderivative essentially mean the same thing. So then if I antidifferentiate each of these, the antiderivative of e to the x is e to the x. The antiderivative of cosine of x is positive sine of x. And the antiderivative of x squared, again, using the anti-power rule, is x to the 2 plus 1 divided by 2 plus 1. And then we don't write plus c plus c plus c each time. We just write 1 plus c at the end, because all those constants can be just one constant. Sometimes people prefer to write this as 1/3 times x to the 3rd. Either way is fine. But normally, I would not write this step here. I would skip this step completely to say that, like, oh yeah, I know if I'm adding functions together, I'm just going to antidifferentiate each of them and add the results together. The same thing is true for subtraction. The same thing is not true for multiplication or division, right? You can't just, so just to be super extra clear about things. We definitely cannot do the following. The antiderivative of 2x times cosine of x is definitely not equal to the product of the antiderivatives. You can't just antidifferentiate 2x and get x squared and cosine x and get sine of x. And the reason that this doesn't work is because of the product rule. Yeah, I'll back up in just a second if you don't mind. So the reason this doesn't work is because, again, so I'm going to remind you, this is an important connection to know. If the antiderivative of 2x times cosine x was equal to x squared sine of x, then it should also be true that the derivative of x squared times sine of x should equal 2x times cosine of x. But it's not because of the product rule, right? We know how to spell no with a K. We know that the derivative of the product x squared times sine of x is the derivative of the first thing, leave the other thing alone, plus then leave the first thing alone, multiplied by the derivative of sine, which is cosine of x. And clearly, the derivative of x squared sine of x is not equal to 2x times cosine of x. So the antiderivative of 2x times cosine of x is not x squared times sine of x. And we'll talk about later, there is a method for integrating a product like this. It's called integration by parts, which we will definitely get to at some point. But for now, this is kind of something we're not really sure how to antidifferentiate. But just to be really, really, really clear, you can't antidifferentiate the product or a quotient by just doing the top part and the bottom part. So let's go back. I'll do another example of that in just a second. Well, let's go back to the previous example. The way I got x cubed over 3, again, was I'm just using the anti-power rule, that the antiderivative of x squared is x to the 2. I mean, really, it's because the derivative of this is equal to that. I'm getting x to the 2 plus 1 over 2 plus 1, which is x cubed over 3. And the reason that's the antiderivative is because what's the derivative of x cubed over 3? Well, I'm not going to use the quotient rule. I never use the quotient rule if I'm dividing by a constant, and you could, but it's a waste of time, kind of. Instead, I'm going to remember that I can write this as the derivative of a constant 1/3 times the function x cubed. And then when you differentiate the constant times the function just hangs out. And the derivative of x cubed is 3x squared. The 3's cancel, and you just get x squared. So the antiderivative of x squared is x cubed over 3, exactly because the derivative of x cubed over 3 is equal to x squared. Back to this other side here, just to really reinforce this idea. It's also true for quotients. If I was integrating something like, let's see here, let's make something not too terrible, James. X to the 5th plus x squared, sure, plus, sorry, x over x cubed, sure. If I was trying to find the antiderivative of this quotient here, I can't just anti-differentiate each part piece by piece. Right? It's very incorrect to say that it would be. So I've definitely seen people do this. So here's a wrong answer that I don't want you to write down. I mean, you can write it down if you want, but just make sure you know it's the right answer. I can't do the anti-power rule for each of these things. I can't say it's x to the 6th over 6 plus x cubed over 3 plus x squared over 2 divided by x to the 4th over 4. We cannot do that. It doesn't work that way. And again, the reason why is similar to the reason why here. The reason why it didn't work in that first example is because when you differentiated this, you had to use the product rule to get your answer. The same sort of thing is true here. If I was going to differentiate this, I'd have to differentiate it using the quotient rule, which would definitely give me something very, very different than this integral here. Sorry, than this integrand here. So the way we should actually integrate or anti-differentiate something like this, when you have a quotient that's divided by just one power of x, you're going to simplify it first. So this is equal to the integral of, I like to write it this way, x to the 5th divided by x cubed plus x squared divided by x cubed plus x divided by x cubed, and then simplify each of those. Other people prefer to do this. It's x to the 5th plus x squared plus x all times x to the negative 3rd. Be careful if you do it this way. I've definitely seen people somehow magically turn this into x to the 5th plus x squared plus x cubed plus x to the negative 3rd and forget to kind of distribute that, but you have to distribute it. So this is really equal to, either way, x to the 5th divided by x to the 3rd is x squared. X squared divided by x cubed, you could write as x to the negative first, but I'm going to write it as 1 over x. And then x divided by x cubed, well, x to the 1st divided by x cubed, if you subtract those powers, 1 minus 3 is negative 2. So you get x to the negative 2. Most powers I write as x to a power. The one kind of exception is 1 over x. I usually don't write that as x to the negative 1st, and you'll see why in a second here. We also would have gotten the same thing had we, where'd my red pen go? Had we distributed this to each of those terms, right? You just would be adding the powers. 5 plus negative 3 is 2. 2 plus negative 3 is the negative 1st power, or 1 over x. And 1 plus negative 3 is negative 2. And so then when I anti-differentiate this, I'm going to use the anti-power rule, except for the middle part. So the antiderivative, and I'm running out of room here. The antiderivative of x squared is x to the 2 plus 1 over 2 plus 1. I'm going to leave 1 over x alone for a second. And the antiderivative of x to the negative 2, again, I'm just using the anti-power rule and getting x to the negative 2 plus 1 over negative 2 plus 1. All right, plus c, of course. So what's the antiderivative of 1 over x? Well, what's a function we know that's derivative is equal to 1 over x?
ln of x?
Exactly. Well, almost exactly. It's actually not quite just ln. So I will say, for those of you typing ln, if you wrote that in the test, I know you mean ln of x, but you should really type ln of x, like ln space x, just so that you're used to writing it the right way for other things. It's actually, though, and I'll explain this in a minute here, it's actually the natural log of the absolute value of x. And there's a reason for that we'll get into momentarily. But for now, we'll just leave it there. And then you would definitely simplify this. I'm going to write this as x to the third over 3 plus natural log of the absolute value of x plus, this is x to the -1 divided by -1. I would probably write that as minus x to the -1 or minus 1 over x. Either way is fine. Plus c. That would be my final answer. So, really want to make it clear when you're anti-differentiating things, it's good to simplify first if you can. We can't just anti-differentiate a product by anti-differentiating the factors, nor can we do that for a quotient, but right, we have to simplify or do something. Okay. So, I know last week I talked about some well-known antiderivatives. Right, so we know, I'm not going to write them all again because we talked about them already, but we know like all the functions that we know are derivatives of trig functions, we know are antiderivatives. Like we know the antiderivative of, for example, secant of x tangent of x dx is equal to secant of x plus c. Because we know that the derivative of secant of x is equal to secant of x times tangent of x. So any derivative you know, you also know the reverse antiderivative, right? So, yeah. And then there's a couple others. We definitely know that the integral or the antiderivative of e to the x is e to the x plus c, because the derivative of e to the x is e to the x. And then you're not wrong to want to say that the antiderivative of 1 over x is the natural log of x. And it's not so much that this is wrong, it's just that it's not as right as it could be. Now, why does it need to be the natural log of the absolute value of x? Well, I don't want to spend too much time talking about this because it's not a huge point to really focus on, but you should remember this because it is mildly important. So let me back up for a second. Let me erase some things here. Yeah, sure. Let me go to the other side. We'll come back to this then. So the reason that the natural log thing, well, what does it say after secant? So it says secant x tangent x here, and over here it says secant x plus c. So the reason the antiderivative of 1 over x is what it needs to be is because it's really a domain issue. So when we're talking about derivatives for a second, if I said, the derivative of x squared is equal to 2x, we know that the domain of x squared and 2x are both everything, which you can write as a fancy R, or you can write as this. And the graphs look like this. Sure. Here's y equals 2x, essentially, and let's do it in black. There's y equal to x squared. And they both exist everywhere on the real number line. The same thing is not exactly true for the natural log function. So if we look at y equal to natural log of x, well, the domain of that function is not all real numbers. The domain is all positive numbers. And we know the graph. I'm going to erase this graph. I'm going to erase some of this graph. All that there. We know that the graph of the natural log function looks like that. It's the 0.10. I probably have shown you guys this before, but just in case I haven't, if you look at your right hand, there is a nice, if you go over your thumb here, there's a nice natural log function right there. I got my hands, let me put on some lotion. My hands are really dry. Sorry. Okay. You can see that a little bit better, yeah. Now without all the dryness of my hands, you can kind of see, I got a lot of lines, but you can kind of see that there's a natural log graph right there. But there's also like an e to the x graph right there. So useful on your right hand. Gotta be the right hand. If you do the left hand, it's natural log of negative x and e to the negative x. So just be careful. And now my hands are all too moist to hold the pens. Right? Okay. So when you take the derivative, y prime, the derivative of the natural log of x is 1 over x. But here's the thing about derivatives. A function is only differentiable on the domain where the original function exists, right? For a function to have a derivative, the original function has to exist there. So even though normally y prime equal to 1 over x would be defined everywhere except for x equal to 0 and would look like, let me do it in red, if I can look at that. Sure. So y prime equal to 1 over x would usually look like this, right? You'd have this part here, and then you'd have this part over here. But I'm drawing it dashed like that because the derivative can only exist on the same or smaller domain. So the domain here is also everything from just 0 to infinity, just the positive numbers. So when I think about the derivative of the natural log function, I'm thinking about just the right-hand side of this hyperbola, 1 over x. Okay, well, why is that an issue? When you go backwards, right, when you anti-differentiate stuff, the domain of the antiderivative should in some sense be larger than or equal to 0 is not included in the domain. That's why there's a parentheses here. Yeah, if I was using a bracket, 0 would totally be included. So if you anti-differentiate something, the antiderivative should have a domain that is greater than or equal to the domain of the function you started with. Now, here's the problem. So again, here's the integral of secant x tangent x dx equals secant x plus c, in case this wasn't clear. F of x equal to 1 over x normally has the domain everything but 0. It has the usual graph. And so we would like, well, sorry, my picture does not look the best it's ever looked. We would like the antiderivative to have a domain that's at least that big or possibly bigger. Bigger meaning it would include 0 as well. And so the problem is natural log of x doesn't fit the bill. Right? Natural log of just x has the domain only positive numbers. So we know, or somehow I don't actually know how this is derived exactly, but if we look at, say, capital F of x equal to the natural log of the absolute value of x. I'm using capital here to reinforce the idea that, oh yeah, this is the antiderivative. So the way we're going to show that this actually is the antiderivative is by just differentiating it. Now, here's where we have to remember something about the absolute value function. I'm going to remind you guys up over here that the absolute value of x is equal to x if x is positive. Right, if x is already positive, then the absolute value of x is just x, right? Like the absolute value of 5, just 5. On the other hand, if x is negative, like if x was negative 5, the absolute value of x isn't just x. You can't say the absolute value of negative 5 is just negative 5. The absolute value of negative 5 is negative 5, also known as positive 5. But I'm saying negative 5 because the way you take the absolute value of a negative number is to negate it, to turn it into a positive. So the absolute value of x is x when x is already positive, and it's negative x when x is negative to turn it into a positive. So we're going to use that here. So I'm going to rewrite this function as the natural log of just x when x is positive, right? Because if x is positive, I'm just replacing the absolute value of x with good old regular x. And it's when x is negative, it's the natural log of negative x, right? Because if x is, say, -5, right? If x is -5, well, the natural log of -5 is the natural log of +5, and that's perfectly fine, right? You can only take the natural log of positive numbers. So this is how we piecewise define this function. Also, just in case you were wondering, the reason why I included 0 here is because it's part of the function. I didn't include 0 here because we can't take the natural log of 0. So 0 is still not in the domain. All right, and now we're just going to differentiate. So f prime of x, capital F prime of x. Well, we're going to do it piecewise. The derivative of the natural log of x is what? Anybody? Anybody? You can type it. Oh, by the way, here's the attendance link again. Please go fill it out if you haven't already. If you already did it, you're good. So derivative of the natural log of x is 1 over x when x is greater than 0. Okay, what about the derivative of the natural log of negative x? Well, I remember, and you guys remember hopefully, that when you take the derivative of the natural log of some stuff, it's 1 over the stuff times the derivative of the stuff. So it's going to be 1 over the stuff times, what's the derivative of negative x? Oh, it's just -1 when x is less than 0. But look, these are the same. This is 1 over x, and this is 1 over x. So the derivative is just 1 over x whenever x is not equal to 0. So we see that although the derivative of the natural log of x is 1 over x, the antiderivative of 1 over x should really be thought to be the natural log of absolute value of x to get the entire domain that we want. So the integral of 1 over x dx, or the antiderivative of 1 over x dx, is the natural log of the absolute value of x plus c. And it looks like this. So here's my natural log function, right? And then since it's natural log of absolute value of x, it's going to have a mirror image in the y-axis and also look like this. And that's my antiderivative, which makes, sorry, this is getting a little closer. If we think about, this red function being the antiderivative, and this blue function being the original function, which is the derivative of the antiderivative. It makes sense when you think about the slopes, right? So again, if you're thinking derivatives, the derivative should give you the slope of the tangent line. So here, for the red function, we can see that the slopes of the tangent lines are negative, and they're getting more and more negative. And the values of the blue function start negative and get more and more negative. Over on the right side, the slopes of the tangent lines are super positive, right? It's a super steep tangent line right there. And then they stay positive, but they get less and less positive. The values of this function in blue start off super positive and then get less and less positive as we go to the right. So these graphs definitely make sense. Okay, let's see. What else do I have on my list here? Sure. Sorry, there's a weird flash outside. Again, if you have questions, don't hesitate to ask them. I don't need that. All right. So while it's important to be able to anti-differentiate, there's more to integration than just anti-differentiation. And one of the things we typically use integration for, so integration is often most closely associated with, is how we typically, wow, that's a good we there, how we find the area under a curve. And typical notation, so go here. So here's a very general looking function. If I want to find the area under the function and above the x-axis between values a and b, or you could say x equal to a, x equal to b. If I want to find this area here, then the area is expressed. So, well, we'll get there. The way we express the area is the integral from a to b of the function f of x dx. And so this notation here is meant to kind of elicit the idea that you're going from a to b and you want the area under this curve here. And the reason we use the same notation for the integral that we do for the antiderivative is because the way we calculate this antiderivative is exactly, the way we calculate this definite integral, and let me actually write those words here. Oh, pen, come on, you should have put on lotion, it's a bad choice. The way we calculate this definite integral is by anti-differentiating the function and then plugging in whatever the limits of integration are. So this is actually one of the parts of the fundamental theorem of calculus. Fundamental theorem of calculus says that, I don't remember, I think this is usually people vary. Some people call it part 1, some people call it part 2. It doesn't really matter. It's part of the fundamental theorem of calculus. Says that the area under the curve, f of x, between a and b can be calculated by finding the antiderivative of that function and plugging in the limits of integration. B first, a second. Always the top limit minus the bottom limit. So this is capital F of B minus capital F of A. And we're going to use this idea to calculate area under curves and area between curves. So let's do an example that we actually already know the answer to. I want to find the area under the curve f of x equal to 2x plus 5 between x equal to -1 and x equal to 3. And we're going to calculate this in two different ways. The first way, geometrically. So sometimes if the shapes under the area under your curve looks like a well-known shape, like a square or a rectangle or a triangle or a circle or a semicircle, you are welcome to use known formulas for area via geometric, you're welcome to use geometry formulas. So for example, I'm going to draw this. That's the line y equals 2x plus 5. It's got a y-intercept of 5 and an x-intercept of -5 halves. It looks something like this. Maybe I do it too steep here. So let's say there's x equal to 3. And there's x equal to -1. So I'm trying to find this area here. And although there is a formula for the area of a trapezoid, I don't remember it exactly. I would just break this up. I would break this up into a rectangle and a triangle. So for the rectangle, so for the area of the rectangle, what's the base of the rectangle? Well, how far is it from -1 to 3? Anybody? Yeah, okay. Yeah, it's definitely 4. And then what's the height of the rectangle? Well, the height of the rectangle is exactly whatever the height of the function is right here when x equals -1. So I plug in -1, f of -1 is 2 times -1 plus 5, which is 3. So the area of the rectangle is 12. And for the triangle, we know the area of the triangle is 1/2 base times height. The base, I feel like I count my hand. Sorry, one sec. It's killing me. The base is the same as it was for the rectangle. It's still 4. And the height is going to be however far it is from here. We know that this height was 3. 3, yeah. This is point -1, 3. So whatever the height is here. Well, if I plug in x equal to 3, f of 3 is going to be 2 times 3 plus 5, which is 11. So the height of my triangle is 11 minus 3, which is 8. Yeah. So you get 1/2 times 4 times 8, which is 2 times 8, which is 16. And so the total area, which I can write as the integral from -1 to 3 of 2x plus 5 dx is equal to 28. And it's perfectly legitimate to find the area under the curve using formulas we know from geometry. The problems with this are that a lot of the curves are not going to have nice geometry formulas. There's going to be a lot of things that don't end up being triangles or semicircles or whatever. So the way we actually usually going to calculate this, and I wish I had given myself a little bit more room here. I'm going to actually erase this here. So the way we're going to see, we can calculate this using the fundamental theorem of calculus, which is also, this part's called the evaluation theorem, is we're going to say, okay, the integral from -1 to 3 of 2x plus 5 dx, we're going to anti-differentiate the integrand, which is just the inside function of the integral. The antiderivative of 2x is x squared. The antiderivative of 5, so I don't think we've actually talked about this yet, but the antiderivative of a constant is just the constant times x. So when you're anti-differentiating 5, you get 5x, because the derivative of 5x is equal to 5. And the antiderivative of 6 would be 6x, the antiderivative of 7 would be 7x, the antiderivative of natural log of 2 would be natural log of 2 times x, because again, it's just a constant. And then, although I could write a plus constant here, I don't actually need to. So then I like to write it like this. We're going to evaluate this antiderivative between -1 and 3. If you want some notation here, right? This is the function. This is the antiderivative. And then we're just going to plug in the limits of integration. And I'm going to remind you often, it's always the top one first minus the bottom one second. So I'm going to get plugging in 3 squared plus 5 times 3, minus plugging in -1, -1 squared plus 5 times -1. Simplifying, you get 9 plus 15 minus 1 minus 5. That's 24 minus -4, which is 28, which is exactly what we got doing it the geometry way. So I really, really, really want to stress to you, this is correct. The way we can find the area under a curve and above the x-axis. So really you're finding the area between the curve and the x-axis is always by anti-differentiating the function and then plugging in your limits of integration. Top first minus the bottom second. So some more examples. I feel like there was something I really wanted to say right now. Come on, brain. What did you want to say? Oh, I know. Okay. So before more examples, one quick idea here. So I want to differentiate, pun intended, between a definite integral and an indefinite integral. So integral of 2x plus 5, which I know is the same one we just did, that without limits of integration, this just says find the antiderivative. So here, that's x squared plus 5x plus c. Because this notation, this just says indefinite interval. AKA the antiderivative. I should say the general antiderivative. Meaning you throw on the plus c derivative. So when there are no limits of integration, right, we don't have anything there or there, then we know it's an indefinite interval and you're just finding the antiderivative as a function of x. So antiderivative is a function of whatever your variable is. To contrast that, we just did the other one, which is the integral from -1 to 3 of 2x plus 5. And we ended up getting that equal to, I'll show the work again, right? It was x squared plus 5x, evaluated from -1 to 3. We plugged in 3, we plugged in -1, subtracted, and we ended up with 28. So this is called a definite interval. Which is equivalent to saying we're finding the area under the curve. And when you get that, the definite interval should always just be a numerical value or a number. Right? There should be no variables in your answer when you're finding a definite interval. It should always just be some value that's representing the area under the curve. So hopefully that distinction is fairly clear. Indefinite, answer the function, should be a plus c. Definite, answer is a number. You don't need a plus c. Okay. All right. Yeah. And no, okay. So then we can use definite intervals to find areas under curves. For example, what's the area under f of x equal to sine of x between x equal to 0 and x equal to pi? Sometimes people will shorten this notation over here. Sometimes people will just say on the interval from 0 to pi. It's a little more concise to write it that way. All right, so, oh, by the way, I know a couple of you came in late. There's the link to the attendance again. You should probably just bookmark that page, right? If you haven't already, like bookmark it, you can just go there. Don't go there extra, just when we have class. So again, if someone writes this out, someone says the question this way, the first thing I'm going to do is say, oh, I need to write an integral from 0 to pi of sine of x dx. And then 2 steps. Antidifferentiate. Okay. What do you guys think? What's the antiderivative of sine of x?
Negative cosine.
Sorry, I didn't quite catch you there. I heard something, but I didn't quite catch it. Because my wife is being really loud. I'm going to assume you said negative cosine of x, which is totally right. It is negative cosine, right? Because the derivative of sine is positive cosine. The antiderivative of sine is negative cosine. Because what's the derivative of negative cosine? Oh, the derivative of negative cosine is negative sine, which is positive sine. I don't need the plus c, but I do need the evaluation line, or whatever you want to call that, from 0 to pi. This is pretty standard notation. Your professor is probably using it once they get there. And then we plug in our limits of integration. We get negative cosine of pi minus negative cosine of 0. Something to be aware of, which isn't really a problem here, but a lot of times when we plug in 0, like when you have powers of x, you just get zeros back. You don't always get a 0 back though, because cosine of 0 is 1. So here we're going to get negative, what's cosine of pi? Ooh, good question. So real quick, in case you forgot, here's the unit circle. Here's the points on the unit circle. -1. Here are the angles, 0, pi over 2, pi, 3 pi over 2, and then all the way back around to 2 pi. And cosine is the x coordinate, and y is, and cosine is the x coordinate, and sine is the y coordinate. So cosine of pi is going to be the x coordinate at that angle, which is -1. Sine of pi would be 0. And then plus cosine of 0. Cosine of 0 is the x coordinate, which is +1. So you get 1 plus 1, which is 2. So the area under the curve from 0 to pi should be 2. Now I'm going to ask another question, which is not going to be, well, I want to show you something. So what if I said, I don't really want to say it that way. What if I just said, what's the integral from 0 to 2 pi of sine of x? Well, if I do that, I get the same antiderivative, negative cosine of x. Now from 0 to 2 pi. And now here's the thing. I don't really have to go any further to know what the answer is, because I know that cosine of 0 and cosine of 2 pi are the same. So when I subtract them from each other, I shouldn't get 0. Let's double check just to be sure. I get negative cosine of 2 pi minus negative cosine of 0. Cosine of 2 pi is 1. So I get -1. Plus, right, minus a minus is a plus. Sorry, you can't see that. Plus cosine of 0 is also 1. And -1 plus 1 is 0. And so the reason I bring this up is because that doesn't exactly mean that the area under the function is 0 area. That doesn't really seem right, because the area under the function from 0 to pi was 2. So here's what's going on. I think I can erase this over here. Draw a picture. Whoops, eraser, come back. So, pi, 2 pi. And here's my sine function from 0 to 2 pi. Topping on the 1, bottom of the 2. So here's the deal. When I did the integral from 0 to pi, I calculated the area under the curve and above the x-axis. And that area is exactly 2 square units. When I did the integral from 0 to 2 pi, I did the area here and the area here, but here's the problem. When you have area that's underneath the x-axis, it actually gets counted as negative. So when you integrate a function, if you're not accounting for what's above and below, you actually end up counting what's called the net area above the x-axis, which is the positive area minus the negative area. So here, or I should say, it's the area above minus the area below. And since these areas are exactly the same, they end up canceling each other out. So this integral here, the integral from 0 to 2 pi of sine of x, is what's called the net area above the x-axis and below the curve. So the area here is 2, the area here is -2. When you put them together, you get 0. A different way I could phrase this question, which is kind of a pain in the butt. Yeah, I think I want my picture, so I'm just going to erase this. So a way I could phrase this question, so I actually find out how much area there is between sine and the x-axis, I could say, well, I could write it out. I could say, how much area, or yeah, how much area is enclosed between y equals sine of x and the x-axis, also known as the function or equation y equals 0 on the interval from 0 to 2i. Now, we already know the answer. The answer is 4, because there's 2 square units here and there's 2 square units there, and we add them together to get 4. But the way you actually have to kind of set this up is you have to break, if you were trying to actually do this like the long way, you'd have to break this up into 2 intervals. The first integral would be this interval from 0 to pi. So the total area is going to be the area of this first part. And so, and I know this is kind of moving into the next section for what Merck's probably talked about this on Monday, or which is yesterday, is the area between the 2 curves. So the area between this curve and this curve, it's always the top function minus the bottom function. So the area from 0 to pi is going to be sine of x minus 0. The top function, y equals sine of x, minus the bottom function, y equals 0. But then from pi to 2 pi, if I'm trying to find the area here, I'm going to integrate the top function, which is 0, minus the bottom function, which is sine. So it's going to be 0 minus sine of x. So I'm getting, so I know the work is the same as what we've been doing. I'm going to get integral sine is negative cosine. I'm going to get negative cosine of x from 0 to pi, plus 0 minus sine is just negative sine. The antiderivative of negative sine is positive cosine. So I get cosine of x from pi to 2 pi. And now calculating this, I can't put these together because the limits of integration are different. I'm just going to do it the long way. So I'm going to plug in pi and then subtract and plug in 0. So you get minus cosine of pi, minus minus. Once you get more practice with this, you'll start seeing a minus minus and automatically just writing plus. It's not too terrible. And then plus cosine of 2 pi minus cosine of pi. And this ends up being, let's see, minus cosine of pi is negative 1, so negative negative 1 is 1, plus cosine of 0 is 1, plus cosine of 2 pi is also 1, it's the same as cosine of 0, minus cosine of pi is negative 1. So I end up with 1 plus 1 plus 1 plus 1, which is 4. So when you're trying to find how much area is encompassed between 2 functions, you always have to break it up so that you can see the top function minus the bottom function in general. Let's see, so how do you tell it's the top function? Excellent question. One way to tell is by graphing it. So if you graph sine x, right, and the y equals 0 is always going to be on your graph because it's the x-axis, you can totally see when it's above and when it's below. So when I say top function, I literally do mean the function that has a higher y value, and bottom function has a lower y value. Okay, so eraser, where'd you go, eraser? It's literally right where it should be. Sorry. But that's a good question. How do I know which function is top and which function is bottom? Because sometimes you're not going to want to graph the thing because it just, well, graphing takes time. But sometimes it's going to be really, really hard or nearly, I mean, I shouldn't say impossible. It's usually impossible. But it can be very challenging to see on your graph which function has the higher y values on the interval you're looking at. So let's look at an example. Let's say I want to find the area between the curves, the functions. Let's say f of x equal to, let me think for 1 second here, 4x minus x squared. 3. Sorry, 1 second here. And y equals x. So let me double check here. Yeah, okay, that should be fine. All right, so to do this, well, notice I didn't give any limits of integration. If I say I want to find the area between the functions, the first thing we actually have to do is figure out where the functions intersect. So one, we have to find the points of intersection. So I'm going to set the functions equal to each other. Right, so I'm going to do 4x minus x squared equal to x. I'm just going to subtract x. So 3x minus x squared equals 0. Factor out an x. And I get x equal to 0 and x equal to 3. So those are my points of intersection, which means they're going to be my limits of integration. And so I want to do, I'm going to graph this at the end, but I want to try and do it without graphing to show you guys how I think about doing this without graphing. So I know to find the area, it's going to be the integral from the point, from the lower value point of intersection to the upper value point of intersection. And then it's literally going to be what I usually write as the top function minus the bottom function. Now, the question, dx, of course. How do you know which one is on top without graphing it? Well, here's the thing. These functions cross at 0 and 3, and only at 0 and 3. Right? If you plug in 0, f of 0 is 0. G of 0 is 0. If you plug in 3, f of 3 is 3, because you get 12 minus 9. And g of 3 is also 3. So these functions cross at those 2 points, but they don't cross anywhere else. Meaning, if you pick a point between 0 and 3 and plug that in, you can see which function has the larger value, and it'll have that larger value on the entire interval between 0 and 3, because they don't cross anywhere else between 0 and 3. So I'm going to pick 1. To pick x equal to 1, I can see that g of 1 is equal to 1, and f of 1 is equal to 4 minus 1. So in this particular example, f is the top function because it has the higher value at a point that's between the limits of integration. So this is going to end up being the integral from 0 to 3 of f of x minus g of x. Which now, if you look over here, you'll notice we already actually wrote f of x minus g of x, right? So we did f of x and we subtracted this over and got 3x minus x squared. So if you see this, you can just be like, oh, it's just going to be that. Or you could write it out. You can say it's the integral from 0 to 3 of f of x, which is 4x minus x squared, minus g of x, which is just x. I would encourage you, before anti-differentiating, to simplify your integrand as much as possible. So this is going to equal the integral 4x minus x is 3x minus x squared dx from 0 to 3. And I've run out of room, so I'm going to go to the next side of the board. So again, I'll remind you we are finding the integral from 0 to 3 of 3x minus x squared dx. Now we're just going to anti-differentiate and plug in our limits of integration. So in fact, I want you guys to try and finish this. Anti-differentiate each of those and plug in the top limit first, and then subtract and plug in the bottom limit. I have to pee. I'll be right back. So go ahead and try doing that. You should get, and I don't know what you're going to get. You'll get something. It should happen. Going to antidifferentiate 3x. So just like with derivatives, when you differentiate something, you leave constant multiples and you differentiate. For antiderivatives, the same thing is true. When I antidifferentiate 3x, I get 3 times the antiderivative of x, which is x squared over 2, right? This is x to the first. Add 1 to the power, you get 2 divided by the power. Minus the antiderivative of x squared is going to be x cubed divided by the power, which is 3. Evaluating between 0 and 3. So let's see, I'm going to get 3 times 3 squared over 2 minus 3 cubed over 3 minus 3 times 0 squared over 2 minus 0 cubed over 3. Now here's something to be aware of. When you plug in 0, a lot of times everything is going to be 0, right? If the power of x is 0 to a positive power, it's definitely going to be 0. But other things like e to the x or cosine of x, when you plug in 0, you don't get 0. You get 1 or other values. So just be careful. Don't assume that when you're plugging in 0, you're always going to get zeros for everything, because it's a mistake that happens a lot. Here we do, right? All of this is just 0. So I end up with 3 times 9 is 27 over 2. I could do 27 over 3, but I could also just cancel a 3 here and 3 there and say 9. And then I would combine this as one fraction, 27 over 2 minus 18 over 2, which ends up being 9 over 2, or 4.5. So the amount of area under this curve is 9/2 or 4.5 units squared. Graphically, here's what this looks like. So the function f of x equal to 4x minus x squared, which you might factor as x times 4 minus x, is a downward opening parabola. It's got an x-intercept at 0 and an x-intercept at 4. And its vertex would be at 2, 4.
Just a quick question.
Of course. Did
you have to differentiate, like I think you said differentiate, where you like the 3x? No. Because there's a constant in front, because like it's a number in front of it, not just like x squared.
So what I was comparing two things. I was actually saying, so you know how like when you differentiate 3 times x to the 7th, the derivative is 21x to the 6th.
Yeah.
Because the constant multiple just hangs out. And the derivative of a constant times a function is the constant times the derivative of the function, which is just 3 times 7x to the 6th, which is 21x to the 6th. Now, we never show all that work, right? We just say, oh yeah, the 7 comes down, it multiplies the 3, you get 21x to the 6th. But the point I'm trying to make here is that just like when you differentiate a constant times a function and you get the constant times the derivative, the same thing is true when you antidifferentiate the constant times a function. The antiderivative of a constant times a function is the constant times the antiderivative. Go ahead.
That applies like across the board, right? So like whatever number is on like in front of a in front of like an x or like a y, you have to do that.
Yeah.
Okay, thank you.
Yeah, so more generally, just to kind of throw it out there, the integral of a constant or the antiderivative of a constant times a function. This is one of those integral rules that your teacher will or has already talked about. The integral of a constant times a function is the constant times the integral of the function, or antiderivative, either way. So it's a very useful rule we use all the time. Back to this. So here's my downward opening parabola. And then the other function was g of x equal to x. It's probably the easiest thing to graph, right? It's just going through like this. And they intersect at 0, 0, and at 3, 3. And so we just found the area enclosed between those two curves. And we had to do the integral of the top function. Oh, the top function is clearly now graphically the parabola minus the bottom function, which was the straight line. Okay. I do feel like I should go back a tiny bit and talk a little bit more about the other side of the fundamental theorem of calculus. So I'll do a couple examples and then I have to ask you guys a question because I'm not sure I didn't see anything like this in Merck's lecture notes, but that doesn't mean it's not in the homework. So, and there definitely is a quiz question about this as well. Just in general, I don't remember if I wrote this on your guys' quiz or not, but everybody in all my classes, you shouldn't stress too much about the quizzes I'm writing, right? They're, as long as you try to do them, you will get full credit. The whole point of the quiz is just to give you an opportunity to kind of gain more understanding and then let me grade it for you so I can give you feedback on how you're doing. So really, really, like, the quizzes I'm writing should be super stress-free. I don't want you to worry about them too much. I just want you to do them when you can. I know you guys have a lot on your plate, so if you happen to not get mine done, it's not a huge deal. The world will not end. But I would like you to do it just because it's an opportunity for you to kind of get feedback from me on how you're understanding things. All right, so the other part of the fundamental theorem of calculus says something that I've been saying a lot already, that the derivative of the antiderivative is equal to the original function. Now, the way this often gets written, I think, is maybe a tiny bit confusing. But I'm going to write it out anyway because it's kind of the way we write it. They say that the derivative of the antiderivative of the function, sorry, it's a dt, not dx, apologies, is equal to the original function. So here's what I'm doing. I'm anti-differentiating this function. I'm evaluating it between the constant a and the variable x. And then whatever that is, I'm differentiating that and getting back the function I started with. The only difference is in here it's a function of t because I can't use x because x is already being used up there, whereas out here it's f of x. So let me do a very kind of general, no, a specific example, then I'll do a general example. So let's say I wanted to find, now I should say, before I say more, here's the sum up. This is meant to be super straightforward. It's meant to make life super easy. If I see the derivative of the antiderivative of something in here, I know my answer is just the same function, but with x's instead of t's. Also, here's the link to the attendance again. So, if I'm trying to find the derivative of the antiderivative from, what do I want to do here? Something not too terrible. From 1 to x of, let's make life easy for James, 3t squared plus 7 dt. So we have to work from the inside out. So first I'm going to anti-differentiate this with respect to t. So when I anti-differentiate a function, the antiderivative of 3t squared is 3t cubed over 3. But the 3's cancel, and I just get t cubed. And again, right, the derivative of t cubed is definitely 3t squared. And you guys help me out. What's the antiderivative of 7?
7x.
That would normally be right. You're very close, except instead of 7x, it's got to be 7t. Because we're integrating with respect to t, not with respect to x. But yeah, you got the right idea. And then we're going to evaluate this between 1 and x. So now I'm going to plug them into integration. I'm going to get the derivative still, where I haven't taken the derivative yet. That's still sitting out there waiting to be done. Plug in x minus plug in the constant 1 in this case. Okay, now we're ready to take the derivative of all this. What's the derivative of x cubed? It's 3x squared. What's the derivative of 7x? Yeah, I did the easy ones. All right, I just want you guys to answer now. What's the derivative of negative 1 cubed?
It doesn't matter because they're constants, so it'd be 0.
Yeah, well, I wouldn't say it doesn't matter, but it does 0 because they're constants, right? Exactly. The derivative of a constant to any power is just 0 because a constant to the 17th power is still a constant. So similarly, this derivative is 0 and this derivative is 0 because they're both constants. So look, the answer to this derivative, this antiderivative, is the same exact function I started with, except instead of using the variable t, now I'm using the variable x. And that's the whole idea. That does say 7. Yeah. Yeah, that believe it or not, that is a 7. Sorry. And that's generally true. When you, oh, that says 7 times 1, yeah. Because it was derivative of 7, because I plugged in the 1, right? I'm plugging in the 1 for t into the spot right there. So the fundamental theorem of calculus, this part of it says when you take the derivative of the antiderivative of some function, you get back the same function, just with this variable instead of that variable. Now the whole point is that you don't actually have to do it the long way. So if someone asks you to find, say, the derivative of the antiderivative from 5 to x of x to the 4th plus, sorry, shouldn't be an x in there, should be a t in there. It's a common mistake that teachers make. T to the 4th plus sine of t plus secant of t, tangent of t, dt. You can totally do the work. You can anti-differentiate each of those things, and then plug in x and subtract and plug in 5, and then find the derivative, but you shouldn't. The whole intention of this is for you to be like, oh, this is just equal to x to the 4th plus sine of x plus secant of x times tangent of x. That's it. It does make a difference. Yes, it makes it. So actually, the difference is, and this actually speaks to a more general rule. So usually when we think about integrating or finding the area under the curve, we think about integrating from left to right, meaning the bottom value is usually thought of as the lower value and the top value is thought of as the bigger value. So like we've been doing this, like the integral from 0 to pi of sine of x, right? The lower value is usually on the bottom, the upper value is usually on top. If they happen to be switched, it changes the sign. Not to be confused with sign. It changes the positive or negativeness of your answer. So if I did the integral from pi to 0, I would get the opposite, right? So it would be sine of 0, it would be negative cosine of 0 minus negative cosine of pi, right? You plug in you do them in the reverse order. And subtracting things in the reverse order changes the sign of what they are. So whenever you change the order of the limits of integration, you're always changing it from positive to negative or from negative to positive. So for this one, typically the way the rule works is you just say, okay, if I'm doing the derivative of the integral and the x is on the bottom and the constant's on the top of the same thing, the shortcut is just to say that it's negative of what you would have gotten. So the answer here is going to be negative x to the 4th plus sine of x plus secant of x, and negative parentheses, all of that. The longer route to get there is say, oh, well, what I'm really doing is I'm saying this is equal to the derivative of the negative of the integral from 5 to x of t to the 4th plus sine of t plus secant of t tangent of t. But then that negative constant, right, that's a negative 1, that can come out in front of the integral, and I'm getting negative 1 times the derivative of the integral, which is just what we know it is. X to the 4th plus sine of x plus secant of x tangent of x. So, short answer to your question, if x is on the bottom, it means you put a negative sign in front of the whole thing. So let me ask you guys a question with the last 4 minutes we have. For those of you that have seen this, which I don't think is anyone in the FAMS class yet, but you guys should see this hopefully soon. I know he's getting kind of bogged down in class, and I understand there's a lot of questions you guys have for him. It's important to ask those questions. I might encourage you to try to ask them in a different venue just so that he has more time to get to the material in class. So try using Piazza. I think he's using it. I know he said he wasn't kind of keeping up with it, but he's going to try to. Or try sending him an email or starting a discussion in Canvas, just because I feel like he's never going to get where he needs to be because of how slow he's moving in class. So that said, if you have questions for him, you should ask them. Just if they can wait till a different place, try to let them so that he can get through more material. Oh, so let me ask you guys, have you seen a question like this? The derivative of the integral from 3 to x to the 4th of cosine of t dt. Has there been one like that where it's not just an x, but like some function of x? Any yeses? All right, I'm not hearing any yeses. I'm still going to do it just because I want you to see one example, but yeah, we'll do one example. It might come up, but they might not focus too much on this. So let me just show you how this one works. It's slightly different, but still the same idea. So this is really just the chain rule. I'm going to plug in the x to the 4th, but then I don't have to multiply by the derivative of x to the 4th. So I know that the answer is going to be cosine of x to the 4th times the derivative of x to the 4th, which is 4x cubed. Now here's why. Well, with this one we can do the long process. I can also say, well, I'm going to antidifferentiate this. I'm going to get the antiderivative of cosine of t is sine of t, evaluated between 3 and x to the 4th. Plugging in the limits of integration, I get the derivative of sine of x to the 4th minus sine of 3. Okay, now let me ask you guys, what's the derivative of sine of x? Everybody says?
Negative cosine of x.
Oh, that's the antiderivative. But I'm actually asking for the derivative here, which is just positive cosine. So the derivative of sine of x is cosine of x. The derivative of sine of some stuff, using the chain rule, is cosine of the stuff. But then what do I have to multiply by?
Derivative of stuff.
Exactly. Minus, what's the derivative of sine of 3?
Zero.
Thank you. Yes, definitely 0. Because again, there's no variables there. That means it's just a constant. Right? If you don't see an x in your thing, it means it's a constant. It means its derivative is 0. So look, we exactly get cosine of x to the 4th plugged in for t, but then you have to multiply by the derivative of this if it's something other than just x. And that's the chain rule version of the fundamental theorem of calculus, part 1 or 2, whichever one it is. You might not have to do this, but I wanted to show you guys one example in case it comes up later. So if you do see this in class, maybe start a discussion to let me know, or tell me on Thursday if you've seen it by then, so that we can do a couple more examples. But if you don't sweat it too much. All right, I think that is all we have for today. I'll just remind you, feel free to start a discussion in Canvas if you want. You're also welcome to shoot me an email, but if you think it's something that other students might benefit from seeing, start a discussion. I think that's the better way to go. There's the attendance document again. Please make sure you fill it out, but only fill it out once, just one time. And I think that's all. Hope you guys are doing well. I will see you on Thursday. Take care.
Thank you.
You're all very welcome.